Now let us talk about software design in Introduction to Software Engineering. In this, we are going to see this introduction to software design today. The goodness or the wellness of design, then functional independence, cohesion and coupling, and differences of function-oriented design with object-oriented design. Then we'll summarize it. So, first of all, what this design phase does, there are two phases prior to this: feasibility analysis, and then comes the software analysis and specification. The design phase transforms this SRS document, which is prepared in the second phase, into a form which is easily implementable in certain programming language. So, SRS document, we apply design activities and we convert or try to convert this SRS document into design document. What about items designed during design phase? What are the items here? First is you will prepare or make module structure. Then you have control relationship among the modules, and these are actually they are a relationship, or they will invoke relationship or call relationship. Then interface among different modules. So we are talking about various modules. So module, what will be the structure of this module? Then the control relationship among these modules. Then interface among this module. That is the data items which are going to be exchanged. So all this needs to be taken care along with this data structure of individual modules. Each module will have certain data structure. And finally, the algorithms for individual modules. So right from the initial point, data, this data to data structure, till the point we are talking about algorithm of these individual modules, all these things are created. So what are good software designs? What you will regard as a good software design? First is, there are series of steps and iterations. Good designs, it comes with a series of steps and iterations, and design activities, they are often or they are usually classified into two: design or high level design. So there are two, we can classify it into two stages, design activities. Then we have detailed design. So preliminary design and the detailed design. And what are the meaning and scope of these two stages, like the high level or low level design? They very different. They are very different from one another, right? They are not just like you have one design and just a more expanded form, but they have very specific things in them. And what about high level design? The outcome of high level design, first is high level design, then we will talk about low level design. So the outcome of high level design will be our software architecture. High level design will give rise to software architecture. And there are several notations that are available to us to make a high level design or to represent a high level design. First is tree-like diagram. We call it as structure chart. So structure chart is used to represent high level design in software engineering. There are other notations also, like Jackson diagram or Vernier or diagram. This may also be used. What about detailed design? For detailed design, for each module, we design in detailed design first data structure, and then we design algorithms. This is very important part of software engineering. So this includes computer science also. In computer science, you will learn a different subject of data structure and a different subject for algorithm design and analysis. So software engineering is considered to be, an amalgamation of various fields which are combined, and they are acting together in tandemness to make a good software. What about outcome of detailed design? The outcome of detailed design will give us module specification. But how to distinguish between a good and bad design? When we are not aware that the software is good or bad, how we are going to tell? We cannot possibly design one. Means unless we know what a good software design is, we cannot possibly design. Unless you know that what you are going to make in a proper form, how you are going to make it in proper form. You will make first, and then you will go to the user, he will point out various problems, then you will come back again. So these problems, how to make these problems minimum at the first go? That is only possible if you have a good software design. So there is no unique way to design a system. There's different methodologies you can adopt. But even using this same design methodology, there are various people, like we have different software people, engineers, that may arrive at different design solutions. So everyone has their own style or own thought. But we have to be very specific when we try to distinguish between a good and bad design. So what is a good software design? A good software design should implement all functionalities of the system correctly. First is all and the other is correctly. And this, it should be easily understandable. It should be easily understandable. It should be efficient. You cannot have a good design if your algorithms are inefficient. And should be easily maintainable, means amenable to change. Easily maintainable. And what is a good software design? What is a good software design? Again, you have to have understandability, or you can understand of the proper design, which is a major use, because it determines goodness of design. A design that is easy to understand. Once you are aware of the design, then you can easily maintain it anytime, and you can verify and change and modulate, modify. So there are so many things involved with understanding a good software, a good design. But if you are not aware of the design, you are not able to understand the design, then of course maintenance will be very hard, very tough. We already know that about 60% effort is spent in the maintenance activity. If you're not aware of the design, if you can't understand the design, then maintenance effort would increase the time which is given for the actual software making. So we have to be very careful about this. But what exactly I mean when I say understandability? I mean use consistent and meaningful names for all the design components, for various design components. And design should consist of cleanly decomposed set of modules. There has to be a modularity, as we have seen in our structured way of programming, that each module should be well made and well connected also. So we'll talk about cohesion and coupling in a short while. But for now, a cleanly decomposed set of modules a good solution would tell. And these modules, they should be arranged in clean or proper hierarchy, like a neat tree-like diagram. So modularity, module means module, procedures, the function. These are all the same name of they are synonyms actually in computer science. So modularity is a fundamental attribute of any good design. What it means: decomposition of a problem cleanly into modules. For the modules are almost independent of each other, and we employ divide and conquer principle. Okay, we have a work, we divide and conquer, and these two should be as independent or as not related with other. So if modules are independent, then modules can be understood separately, individually. And again, if this happens, then the reduction in complexity will automatically come. And to understand why this is so, why? Because it is very difficult to break a bunch of sticks, but it is quite easy to break the sticks individually. So the real life saying also hold here. Then what about clean or non-clean decomposed modules? How can you signify that this is a cleanly decomposed module or this is not? So these are clean modules, decomposed. See, one module will decompose into two parts. These are three parts. So it's so clean. It is looking. You can view it. You can observe it in a clean manner. What about this? So clumsy, so unorganized and non-cleanly decomposed modules. So in technical terms, modules should have high cohesion and low coupling. If I talk about a train, right, then the bogies or the compartments are linked together. This is called coupling. Actually, the word is used there also. Coupled. They are coupled together. They are coupled together. So what we want is, we don't want them to be coupled, or we want low coupling. But what inside is there? We have chairs. They should be so strong, or these there has to be some in between path, so that people can go and come. You should have some arrangement so that the people inside, they have very good interaction first of all, and they can move around freely. For that we need high cohesion. So cohesion means what is going inside, while coupling is between two compartment, you say. If I should not say this, but in the case of any accident, if you have a high cohesion, means if this compartment is well built, this compartment has high cohesion, then this is not going to be affected more. And also we want the accident to cause as less casualty as we would want. For that, if these are loosely coupled, then if impact is here, this is not going to be affected. So just by the analogy of a train and the bogies and coupling between them, you should have high cohesion and low coupling in a module. So we'll talk about them in greater detail. But neat arrangement of modules in this hierarchy, which I just showed you in the diagram, it means low fan out and abstraction. Low fan out. So what is fan in and fan out? Fan in and fan out means how many links this module is giving way or providing. What is fan in? How many links are coming inside? So these are fan in and fan out. And what about abstraction? If you have a neat arrangement of modules in a hierarchy, then we say that these modules are independent of each other, they have proper abstraction. But what about cohesion and coupling? Let me revisit it. Cohesion is a measure of functional strength of a module. What the module is supposed to perform and how it is performing and how well it is performing is cohesion. So a cohesive module performs a single task or function. And coupling between two modules, it is actually a measure of degree of interdependence or interaction between these two modules, which you want as least as possible. A module which has high cohesion and low coupling, they are functionally independent of one another. What do we mean when I say functionally independent? It has minimum interaction with other modules. So they are independent, though they are connected, but still they are independent. So what is functional independence? You have better understandability. You have a good design. And of course, the complexity of the design will be reduced considerably. And where there will be different modules which you can easily understand in isolation. And the modules are independent, of course. So functional independence, that it reduces the error propagation also. How? The degree of interaction between modules is quite low. You don't have much interaction. And the error which is existing in one module is not going to affect the other modules. It may affect, but not so much. And if they are functionally independent, it will not. And then if they are functionally independent, you can reuse the modules as and when required. So a functionally independent module, this can be easily taken out and used in different programs. So this is how we achieve reusability. And each module does some well-defined and precise functions. And the interfaces between the modules, means among the modules, they are quite simple, minimal and understandable. But there are no ways to actually quantitatively measure the degree of cohesion and coupling. This is you can classify or classification of this different kind of cohesion and coupling. This may give us some idea regarding the degree of cohesiveness of a module. And what are these called classification of cohesiveness? Again, I'm saying that you don't have any quantitative measure, but still it is somewhat subjective. But gives us some idea about the cohesiveness of a module. Just by examining the type of cohesion exhibited by a module or presented by a module, we can roughly tell whether it displays high cohesion or low coupling, and only the experienced eyes can very well tell. So these are the classification of cohesiveness, cohesion: functional, sequential, communicational, procedural, temporal, logical, and coincidental. These are the classification, and this is how our degree of cohesion would increase. If we have functional independence, functionally they are cohesive, then we say the degree of cohesion is very good in the particular module. So what is this? There are various classification. Let us see coincidental cohesion. The module performs a set of tasks which relate to each other very loosely. These are coincidental cohesion, if at all. The modules, they contain random collection of functions, and functions have been put in the module out of pure coincidence, without any thought of design. That is why it is in the bottom of the classification. Then we have logical cohesion. What does this mean? All the elements of the module, they are performing similar operations, like error handling, data input, data output. For example, if we talk about logical cohesion, a set of print functions to generate an output report arranged in a single module. So this can be an example of logical cohesion. Temporal cohesion means the module contains tasks that are related by the fact. They are related by some fact. And all the tasks must be executed at the same time span. That is, we are calling as temporal cohesion. And what may be the example? A set of functions responsible for, say, initialization, startup and shutdown of some processes. Then procedural cohesion, a set of functions of the module, all part of a procedure, that is algorithm. Certain sequences of steps have to be carried out in certain order to achieve an objective. For example, the algorithm for decoding a message. These comes under procedural cohesion. They are cohesively procedural wise cohesive. So communicational cohesion, all functions of the module, the reference or update the same data structure. This is communicational cohesion. The set of functions defined on an array or a stack, right? This is an example. But please mind that we want, whatever I'm talking about this cohesion, we want as less or least cohesion as possible. Then we have sequential cohesion. That means elements of module form different parts of a sequence, and output from one element of the sequence is actually an input to other. Like, sort, search, display, all these are sequentially cohesive. And functional cohesion, different element of a module, they must cooperate, or they are cooperating. They must, I should not say must, because we want this cohesion to be as least as possible. In this case, if we see functional cohesion, that means different elements of a module, they cooperate just to achieve a single function, or for example managing an employee's payroll. And when a module displays functional cohesion, we can describe the function using a single sentence, right? And how to determine this cohesiveness? Just write down a sentence to describe the function of the module. Like, if the sentence is compound, it has sequential or communicational cohesion. So just you have to write a sentence to describe a function. If you just have to see the English. If this grammatically compound, if the sentence is, then it has sequential or communicational cohesion. If it has words like first, next, then, after, then it has sequential or temporal cohesion. If it has words like initialize, then we have temporal cohesion. So this is how we can easily determine the cohesiveness. Now coming to coupling, what it does, coupling indicates how closely two modules they interact, or how interdependent they are, as I just showed you in the example of a train. And the degree of coupling between two modules, it depends on their interface complexity. So there are no ways to precisely determine coupling between two modules. But classification of different type of coupling will help us to approximately estimate the degree of coupling between two modules, as we just saw in cohesiveness. So there are 5 types of coupling that can exist between any two modules. And what can they be? There are classes of coupling, that is data, stamp, control, common, and content. And in this way, this degree of coupling is increasing. So please mind, we want coupling to be as least as possible. We need to have a clear hierarchy. So control hierarchy, which should represent the organization of modules. And the control hierarchy, we also known as program structure. And in common notation, we have seen in the form of structure chart, a tree-like diagram to represent this. It clearly shows the neat hierarchy. And what about neat arrangement of modules now? This means low fan out and abstraction. This also we have seen. So what would be the characteristic of module structure? First is your depth, then we have width, and then fan out. What is depth in module structure? The number of levels of control. In width, we have overall span of control. These are the controls, if you have a program, then how the controls are changing. Or if you have modules, how these controls are changing in the program. What about fan out? This is a measure of number of modules which are directly controlled by a given module. This is one module, this is the second module. You have 2 more modules. If this module is controlling these 3, then we say that the fan out of this module is 3. And what about fan in? Just reverse of fan out. This indicates how many modules directly invoke a given module. So if this is a module and it is invoked by, say, these 2 modules, then we say that the fan in of this module is 2. But high fan in, it represents code use and it is encouraged. So we need to have high fan in. And what about fan out? This fan out, the measure of the number of modules which are directly controlled by a given module. We'll talk about that. But for now, fan in, we need high fan in. Then again, with the reference to goodness of design, a design having these modules with high fan out numbers is not a good design. So we need less or least fan out. And you have known what fan out means. So a module having high fan out, it lacks cohesion. It lacks cohesion. If module is this and it has number of modules, and it is fanning out these number of modules, then we say that the fan out is high and it lacks cohesion and it is not good for our design. A module that invokes a large number of the other modules, that is high fan out, this is likely to implement several different functions, and it is not performing its own function. It is likely to perform a single cohesive function. It is not likely. And coming to this control relationship, a module that is going to control another module, which is said to be a superordinate to it, because it is controlling another module. In other terms, a module controlled by another module is said to be subordinate. So these are two modules. This module controls this module. This module is superordinate, and this is the subordinate module. Then coming to visibility and layering, we say that module A is said to be visible by another module B. A is visible by B if A is directly or indirectly calling B, because it is calling, so it is visible. On layering principle, it would require modules at a layer can call only the modules immediately below it. There are various levels. So this should call this layer and this should call this layer. What about abstraction? Abstraction means the lower level modules, they do input, output and other low level functions. And upper level modules, they do managerial functions. Upper level managerial, while lower level input, output and low level functions. So what would we want with a good design? The principle of abstraction requires these lower level modules doing input, output and low level functions do not invoke functions of higher level modules which are doing managerial activities. This is also known as layered design. We have talked about higher or high level design and low level design. So the high level design, it maps some functions into modules, which is this FI function and these other modules, such that each module has high cohesion. Coupling among these modules, they should be as least as possible, and there has to be a neat hierarchy. So modules need an organization into a neat hierarchy. So two fundamentally different software design approaches are there. One is function oriented design, the other is object oriented design. We know about this a lot because people who are watching this, they are well aware of object oriented design and object oriented programming. But these two design approaches, they are radically different. They are quite different, but complementary as well. That means rather than competing techniques, they are complementary to each other. And each technique is applicable, or you can apply it at different stages of design process. They are complementary also. Let us start with function oriented design. So function oriented design, we look the system as something that is performing some function, FI. Okay, some function. And starting at this high level view of the system, these functions, they are subsequently or progressively refined into more detailed functions. So we divide them into more detailed functions. And these functions now, divided functions, they are mapped to the module structure, which you just saw. For example, let us take a function called create new library member. What it does, it creates the record for a new member, assign a unique membership number and prints a bill towards the membership. And this create library member function, it consists of the first one, right? It create new library member function has some sub functions. First is to assign a unique membership number, then create membership record and print bill, because it is actually doing these three tasks. So we have to have three sub functions. And each sub function, which you just saw, three of them, they are split into more detailed sub functions and so on and so forth, till the time the function organization is good and we find a good cohesiveness. So the system state is centralized and it is accessible to different functions which we have divided. And these member records, for example, they are available for reference and updation to several functions like create new members and delete member and update member record, just for member records. So several functions, this for function oriented design, there are approaches that have been developed. We have structure design, Jackson's structure design, Warnier or Ritz stepwise refinement, and Hatley and Peabody methodology. Now coming to object oriented design. We assume or view the system as a collection of objects, that is real world entities. This system state is then decentralized among these objects, and each object manages its own state information. So object has its own responsibility of management of various states. For example, if we have a library automation software, then each library member is a separate object, and it all objects, each object, I must say, has their own data and functions. And these functions, they are defined for one object and cannot directly refer to the chain data of other objects. So one object, own data and function, one function, object can call this function. So there it is, all the objects are going to call those functions. And they're not going to change the data of other objects. So objects have their own internal data and which define their state. And these similar objects, they constitute a class. If we have number of objects, these three are similar, these three are similar. So this represent one class, this represent the other class. And each object is a member of some class. It has to be. And classes may inherit features from superclass, because if I have this class and this class, inheritance may occur from superclass. So object, they communicate by method called message passing. They communicate through message passing. So what is the difference between object-oriented and function-oriented design? So unlike for this function-oriented design, which we just saw in the former part, in object-oriented design, the basic abstraction is not function, like saw, display, or track, but real-world entities such as employee, picture, machine, radar, system. This is the difference. And in object-oriented design, the software is not developed by designing functions like update employee record, again employee address. This is not done, but just by designing objects such as employees and departments. So first we talk about objects, we make a class, and then we talk about functions. Grady Booch, he sums up this fundamental difference. He says that identify verbs if you are after procedural design, and nouns if you are after object-oriented design. Object-oriented design, nouns that are real-world entities, objects. Procedural design, functions or verbs they perform. So in object-oriented design, state information is not shared in a centralized data. This is very important. But it is distributed among the objects of the system. This is what happens in the object-oriented design. Just take an example. Say in employee payroll system, these can be the global data, like the name of the employees, their codes, and their salaries. But in object-oriented system, the data is distributed among different employee objects of the system. An object, they communicate by message passing. So one object may discover the state information of another object by just interrogating it through message passing. Somewhere or the other, the functions must be implemented. So the functions are usually associated with specific real-world entities, which are called objects, and they directly access only part of the system state information. So function-oriented techniques, they group functions together, if and only if, as a group, they make them as a group, and they constitute a high-level function in function-oriented techniques. But in object-oriented techniques, the group function together on the basis of the data which they operate on. Not on the functions, but their data they operate on. To demonstrate the difference between object-oriented and functional-oriented design approach, we have automated fire alarm system for a large building. So, we need to develop a computerized fire alarm system for a large multi-story building. We have 80 floors, 1000 rooms in the building. Different rooms of the building, they are fitted with smoke detectors and fire alarms. And this fire alarm system, they are going to monitor the status of the smoke detectors. So whenever a fire condition is reported by any smoke detector, the fire alarm system should determine the location from which the fire condition was reported and then sound the alarms in the nearby or neighboring locations. So the fire alarm system should flash an alarm message on the computer console, and firefighting personnel or the people who are addressing this, they must console round the clock. So after a fire condition has been successfully handled, the fire alarm system should let the firefighting personnel to reset the alarm. Let us take, we have seen the example or the problem. Now, function-oriented approach, what it is going to do, we have certain global data or these system state which are accessible by various functions like detector status, detector locations, alarm status, and this alarm status will be activated when the status is set. This is alarm focus, room number when the alarm is located, and this is the neighbor alarms which each detector has at most. Right? We have 10 neighboring alarm locations, and the functions which operate on the system state, these are like this: interrogate detectors, get detector location, determining the neighbor, ringing alarm, resetting alarm, reporting the fire location, as we have seen in the problem statement. While in object-oriented approach, we have a class detector. We have attributes like status, location, neighbors. We have operations like functions to create, sense status, and get location, and to find neighbors, of course. The class alarm, we have class detector. First class is detector. Second class is our alarm. In this, the attributes would be, the fields would be the location and status. The functions in this, the operations as we call it, can be create, ring alarm, and get location. And then we have reset alarm. So in the object-oriented approach, a program, appropriate number of instances of the class detector and alarm should be created. So in function-oriented approach, the system state is centralized. Several functions accessing these data are defined. While in object-oriented program, the state information is distributed among various sensors and alarm objects. So use object-oriented design to design the classes. Then apply top-down function-oriented techniques, because these two are complementary, just to design the internal methods of the classes, because classes consist of attributes and fields. So a system may appear to have been developed in an object-oriented fashion, but inside each class there is a small hierarchy of functions designed in a top-down manner, because again, let me reiterate, they are complementary. Though they are radically different, they are somewhere related. So I hope you found the difference between these two. So when we started this discussion, we talk about activities undertaken during software design phase. We have identified the information need to be produced at the end of the design phase, so that the design can be clearly and easily implemented in some programming language which you choose. So we characterize the feature of good software by introducing the concepts of fan in, fan out, cohesion, coupling, abstraction, etc. And we classify different types of cohesion and coupling, and that enables us to approximately, not in a quantifiable manner, but approximately determine the cohesion and coupling existing in a design. And there are two different approaches to software design. First is function-oriented approach and object-oriented approach. And we saw the essential philosophy between these two approaches. And these two approaches are not competing, but they are actually complementary to each other. So this was about design by Dr. RAJIB. And I hope you got a detailed idea about the software design. Thank you so much. Take care.